So thanks again for coming to another of our public talks. I'm Chris Smink. I'm the director of the Rotman Institute, and the Rotman Institute, in collaboration with the Department of Philosophy, hosts these events each fall in October. So this is the second in our series. The next two talks, one is about the cinema. Final week, Stefan Kohler is talking about memory and from a neuroscientific perspective. So this week we get to have another talk which is on the nature of time in physics, and it's a real delight to introduce my colleague Robert DiSalle, who has been studying space and time and their role in philosophy and physics for years. It's the focus of a great book that he wrote, Understanding Space-Time, which was published I think in 2003 or thereabouts. It's a really fine text. It discusses how the problems and the understanding of space and time have been a central issue in physics and natural philosophy since the 17th century. So ever since physicists have been interested in understanding how things move and how we can discover things about the world by clarifying how things move and what causes their motion, a central question in that quest has been, how do we characterize space and time? And Robert's work has shown how the concepts of space and time have evolved from the 17th century forward to the 20th century. And today we're going to hear about why it is that we should think of these two as intertwined, why physicists have come to talk about space-time rather than space and time separately. And so without further ado, it's a real pleasure to introduce Robert DiSalle.
Thank you. And so I'm going to talk about space and time intertwined. So my starting point is really the idea that we all know from modern physics that space and time are intertwined, that space-time is one thing. So I'd like to ask a couple of questions. How does that relate to our common sense view of space and time? And where does our common sense view come from? Why did we ever think that space and time are two separate things? So this is actually a surprisingly deep question in the philosophy of physics and in the theory of knowledge generally. Like, how do we know what the structure of space is in ordinary life? And what was it that compelled mathematicians and physicists to think of space and time as just one thing, space-time? Yes.
Was that a question you want someone to...
Oh, no, I'm going to answer that question, I hope.
I thought you wanted speculation. Okay.
Well, you can speculate at the end,
Okay.
if you don't like my answer.
No, that's fine.
So, how do you scroll down? Did I just scroll down?
You just scrolled them. Yeah.
Okay. So, the idea of space-time as we now think of it in special relativity comes from a great mathematician who wrote a paper soon after Einstein discovered special relativity with a new way of thinking about the special theory of relativity in what he called the absolute world, the world in space and time. And he said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So that might seem to suggest to you that our separate understandings of space and time are illusions in some way, that time isn't distinct anymore. It's sort of blended in with space into a four-dimensional entity. In fact, he says three-dimensional geometry becomes a chapter in four-dimensional physics. And now you will perceive why I said at the beginning that space and time would fall away into the shadows, and only a world in itself persists. So I'd like to try to help you understand, first of all, what is this very strange, abstract-sounding idea? Where did it come from? And how does it relate to our ordinary way of thinking about the distinction between space and time? Because understanding time, I think, is part of understanding how space and time are different. That doesn't work. Scroll down. What makes it go down? Anybody?
There you go.
Oh, it did go down. So I think of this as part of a bigger question about philosophy in general. Do we ever really make progress in philosophy, or have we been arguing about the same things for 2,500 years? And the answer to that is yes, we have been arguing about the same thing for 2,500 years, and we make progress. We don't come to a final stage where we have all the answers, because part of the answer we come up with to questions like this, especially about the nature of knowledge and the nature of knowledge of the physical world, such as space and time, depends on what we learn about the world as we go along. So an answer that we abandoned because we don't believe in Newtonian physics anymore was a good answer at the time, but we needed a better one in light of things we learned about physics since the time of Newton. So you could ask all these questions, right? Does this mean they're matters of opinion? No. They're matters of rigorous inquiry where we actually figure out things and clarify concepts like space and time. We just don't come to final answers because the sciences aren't through telling us things that we don't already know about the nature of space and time. So you might take this question to be a classic example of a philosophical question that might seem like something only to discuss in an undergraduate classroom, or when you're intoxicated with a bunch of friends, or when you've been accused of a crime. Well, is there really an external world outside of our minds anyway? How many of you have asked the judge that question? Well, is it all just an illusion taking place within our minds? Well, that sounds like a silly question, maybe, but it's an important thing to try to understand. What is our concept of a world outside of our minds? Where does it come from? A world out there in space. Why do we have a concept of a world outside of us in space? That's something that philosophers thought about over centuries and actually came to real clarification about, something that I would say we understand better than the first people who posed that question. And not only that, but understanding it was very relevant to progress in our understanding of the world itself out there in space. Why it didn't work before. Yeah. So anyway, Einstein, in addition to coming up with the theory of special relativity, the theory of general relativity, and much of what we know about quantum mechanics, really taught us a lot of what we know about the philosophy of physics, because he was one of the people who explained what a lot of previous scientists like Newton, Maxwell, Galileo knew implicitly, which is that sometimes you can't make progress in science without thinking out philosophical problems, thinking through the concepts that you're using. And this is why Einstein made this remark that it's often said that the man of science is a poor philosopher. So why shouldn't the physicist just let the philosopher do the philosophizing? Well, it might be the right thing at a time when the physicist believes he has at his disposal a rigid system of fundamental concepts and laws which are so well established that waves of doubt cannot reach them. But it cannot be right at a time when the very foundations of physics itself have become problematic as they are now. Now was 1936, but I think this applies equally well to all the groundbreaking work that Einstein did starting in 1905. We can't just surrender to the philosopher the critical contemplation of theoretical foundations. So that's the kind of thing I'm going to talk about this evening. Now, this is another famous quote from Einstein, I think. I think it's famous. The whole of science is nothing more than a refinement of everyday thinking. So he concludes from this that the scientist can't proceed without considering critically a much more difficult problem, the problem of analyzing the nature of everyday thinking. And what I hope you'll see by the time I'm done is that these seemingly abstract ideas about space-time have come to be understood through what really can be called an extension of everyday thinking. That in some sense, even the special theory of relativity doesn't go against common sense or violate common sense. It just teaches you to put common sense in a bigger context. See how different common sense points of view fit together into a bigger picture. Common sense can tell you a lot about what's around you in space. It can't necessarily tell you something about the large-scale structure of space. Common sense tells you almost everything you know about time. But it doesn't necessarily tell you how your local conception of time integrates with another conception of time from another observer. And that's where common sense has to be refined and extended into a larger theoretical picture. Yeah. I just want to give, this is, I think, a very good example of science as an extension of common sense. Figuring out that the Earth is not flat. I know I'm from the United States, and back in the old country, there's a lot of people who think that this idea comes from faked photographs by NASA, and that it takes really complicated, mysterious, conspiratorial government agencies to convince people that we live on a sphere. But the ancient Greeks figured it out about 2,500 years ago by what I would call an extension of common sense. And it's an aspect of a curved surface that is just simply isn't true on a plane, that if you say put up a flagpole that's perpendicular to the surface in one part of the surface, and if you go to another part and put up another perpendicular stick or flagpole, the two of them will not be parallel. On a flat surface, of course, they would all be parallel. On a curved surface, they wouldn't be. Knowing that is one of the ways in which you can think of comparing the surface of the Earth to straight lines in the geometry of the surrounding space. So I think maybe one of the first notions that people had of the Earth being a sphere was from seeing the shadow of the Earth on the moon during an eclipse. Of course, you could conclude from that that the Earth is a disk and not a sphere. Although you couldn't conclude that if you really compared every observation of an eclipse from every angle. But one of the things that was more obvious, even to common sense, was the notion that ships disappear over the horizon, right? Instead of getting smaller as they move away, they actually go below the horizon because the Earth curves away from the line of sight. And that's a kind of, you have a local picture of the Earth in which it looks flat, and that seems like common sense, but it's not a violation of common sense to say that it's curved. It's just a comparison of two different, or several different, or many different common sense points of view. And this is how they actually figured out not only that the Earth is a sphere, but how big a sphere it is. In roughly 240 BC, if you know, it's kind of like the flagpole example, right? If you have something perpendicular to the Earth in Syene and perpendicular to the Earth at Alexandria, or any two places at different latitudes on the Earth, you can just compare what is the direction of the sun at noon at one part of the Earth from the direction of the sun at noon at a different part of the Earth, and ask if I can figure out the angle between those two, and if I assume that the circle has 360 degrees, then I know that the size of the Earth, the ratio between the size of the Earth and the distance between these two places is the same as the ratio between that angle and 360 degrees. And they came up with an estimate based on their best estimate of how far these two places were apart, that the Earth is approximately 40,000 kilometers in diameter, in circumference, excuse me, which isn't really bad. Again, it really is an extension of a common sense idea that if you're on a curved surface, two perpendiculars won't necessarily be parallel to one another. So now that's just an example of what I mean by relating a scientific theory to common sense. I'd like to just talk about the theory of relativity that Einstein came up with in 1905, because that's what has called a traditional conception of time into question. And I'd like to start off by pointing out, it became common to call Einstein's theory the theory of relativity. After he came up with general relativity, then it started being called the special theory of relativity. But the fact is, there had been a theory of relativity around for about 200 years before Einstein wrote his famous paper on special relativity. It was a good theory of relativity that worked very well. In fact, that was part of what motivated Einstein. He said, we have a theory of relativity for mechanics. The question was, why don't we have a similar theory of relativity for electrodynamics? What is the classical theory of relativity? Well, we associate it with the name of Galileo for the very good reason that if he hadn't come up with this theory, he wouldn't have been able to persuade people that the Earth is in motion around the sun and that it's rotating on its axis. Because it was a very old argument, and really a good argument, at least a good question to ask. If the Earth is rotating on its axis, why don't we feel it? We don't often give people enough credit for having good reasons for doubting that the Earth is actually in motion. But at least there was a demand for some evidence. What is it that tells us that the Earth is moving? It doesn't appear to be moving. Why doesn't it? So the important thing that Galileo accomplished, which is why we sometimes call this theory of relativity Galilean relativity, is he just pointed out to people that they don't have conclusive evidence whether the Earth is moving or not. Because if you consider, say, a stone falling from a tower on the Earth, it was a very old argument that as the Earth moves, that the stone should not fall directly down to the bottom of the tower, it should be left behind. But Galileo pointed out, well, that doesn't happen on a smoothly moving ship. Why? Well, because once you drop the stone, it continues in the motion that you originally gave it. And this idea that motions can be added together was what Galileo figured out that really nobody else had before. Right? Copernicus gave you good astronomical reasons to think that the Earth is moving around the sun, but he couldn't really answer this question, why don't we feel the Earth moving? He could say, well, you've been on a ship, haven't you? You know, sometimes you don't know if you're moving or not. But he couldn't explain why. And Galileo explained why by explaining how, say, the falling of a stone due to gravity is happening at the same time and is composed with the horizontal motion of a ship along the ocean or the Earth turning on its axis. Christian Huygens is the first one to make this principle precise. He drew that picture. He considered doing an experiment with balls colliding in order to try to figure out the laws of collision by considering taking it as a basic principle that this experiment will happen in the same way if you were doing it on the bank of a canal or smoothly moving along the canal. Holland in that time was a great place to think about these things because you have all these canals where you can think of a ship moving in a very smooth, undisturbed way without waves, et cetera, et cetera. So he said that take it as a basic principle that when two bodies collide with one another, the same result will happen if the experiment is at rest or if the experiment is taking place on that smoothly moving barge. Newton adopted that same principle. He called it a corollary because he showed that it was, in some sense, derivable from the laws of motion. That's not really an important question. And he even extended it in a sort of way, not quite the way Einstein did in general relativity, but in a way that kind of looks forward to that by saying, not only will a group of bodies behave in the same way when they're moving uniformly as at rest, they'll also behave in the same way if the whole system is being equally accelerated by parallel forces. It would behave exactly as if it were at rest. Why would he think of an example like that? Well, it's easy to think, if you imagine a system of planets moving around each other like Jupiter and its moons, the motion through space doesn't affect the actions that these bodies have among themselves. But not only that, Jupiter and its moons are actually being accelerated. They're all being pulled down toward the sun. It's true that they're not being pulled down equally and in parallel directions, because how much of an attraction toward the sun they feel depends on how far they are from the sun. They're not all the same distance from the sun. And of course, the attractions aren't parallel because they're all pointing toward the center of the sun. But Jupiter is so far away from the sun that it doesn't matter. You could say that's a kind of extended relativity principle in the sense that you can say, here's a system of bodies that's not moving uniformly. It's being acted upon by a force, but it's still, you can treat it as if it were at rest. And that's the fundamental idea of relativity and this extended version of it that's peculiar to the force of gravity in the pre-Einstein setting. That's as much as anyone knew about relativity before Einstein. Now, this is a diagram of space-time according to Minkowski. Now, how does this relate to a common sense view of space-time or to a theory of relativity? I have well, that's just something that's from his notebook as far as I know. This is in a published version of it. I don't know if that means anything to any of you who haven't already studied relativity. Sorry. Just saying. Anyway, this is a translation. What does all this mean? So here's a point, O, in space-time. What does that even mean? Well, Minkowski said, no one has ever observed a place except at a particular time. And no one's ever experienced a time except at a place. So he was trying to argue, in a way, all of your experience is four-dimensional. Human events are four-dimensional objects. Just in a simple mathematical sense, that if you want to specify an event, you have to say where and when. Right? You need 3 coordinates to say where you are in space, and 1 to say when in time. And that's not a crazy idea that it takes a 19th century mathematician to come up with. It's just a very moderate extension of common sense. If you want to meet somebody, you have to give them spatial and temporal coordinates. Right? You might say, well, meet me at Dundas and Clarence, then I only need 2 spatial coordinates. But you could be on the 2nd floor of the library, which would mean you'd need that 3rd spatial coordinate, and of course you need the time. Otherwise, it's kind of pointless to try to arrange a meeting with someone. When you talk about a historical event, like if you say, well, I was at Woodstock. I don't know if any of you were, I'm not even old enough to say that. But if I said that, I'd have to mean, yeah, I was at that town in fact, I drove through there this morning. But that's not what anybody means when they say they're at Woodstock. They were talking about an event, and you have to give the space and time coordinates. And if you went there in, say, January 2004, nobody would care. I have no idea what that event was all about because I'm too young, but I understand it's a place that even older geezers than I am like to say they were. But they mean an event, so they mean 4 coordinates. So in a way, Minkowski just was trying to say that's what the world is. The history of the world is something that you have to specify 4 coordinates to specify completely. And there's nothing at all mysterious about that. That's human history. Now, what does it have to do with that diagram? Well, I'll come back to that. Just think about it in your ordinary common sense view of space and time. Well, we have this notion of what's happening now, that's a time coordinate, and we have a notion of what happened at some other time, and we have a notion of different places where we might be. So just think of this, think of each of those 2 grids, right? Of course, all I can do with 3 dimensions is kind of suggest them. I can't even suggest a 2-dimensional space plus time on this, but you're supposed to think of that as a kind of grid of some kind, right? Here's a point that represents, some place at some time, and here we are now. That's where this is the same place earlier, right? Here and then, or here's over there and now, not where I'm standing, but over there, and of course, in that earlier time, you could say, well, there was there and then. Right? There's nothing that goes beyond common sense about this idea, right? We can think of our lives, if we want to, with a mild refinement of common sense, as having this four-dimensional structure. So we can think of the history of the world as the history of space through time. Right? You have to kind of imagine that each one of those planes is supposed to represent space at a given time. And there's nothing counterintuitive about this idea of space-time if you think about it this way, right? S1 represents just where everything was in the universe at time t1. So if we just ask, well, what's happening right now? Where is everything right now? Right? If I took a picture of everyone in this room, then I would say, well, this is a moment that was captured. It was 7:32 p.m. On October 13th, and it was at this exact spot on the Earth. And there might be a different arrangement of things later. There will be a different arrangement of things later, just because I'm standing here, or some of you have shifted positions, right? And so on. And there's a time interval between any two of these surfaces. So the question now is, well, I told you, and some of you already knew, that in special relativity and general relativity, we think of space and time as sort of tied together. What's so convincing about the idea, the common sense idea, that we can separate them? That we can say, well, this is everything that's happening now. This whole idea of nowness, so to speak, the whole idea of the present time is kind of like a divider in space-time that separates space-time, the four-dimensional thing, excuse me, into its natural three-dimensional pieces. So the question of how intertwined space and time are is really a question about how meaningful is it to say of this four-dimensional object that we can objectively separate it into its bits, that space-time really is just space now, with space at the next moment stacked on top of it, space at the moment after that stacked on top of that, right? And then, so to says Captain Ahab once said, all the piled centuries since paradise, right? All of time piled on top of each other as the history of the world goes on. So how should we think about motion? And this is crucial to one of the things I especially wanted to point out tonight. It was this kind of analysis that people had to go through. Why do we think there's an external world? This is actually relevant to that, right? What's the external world? There's a famous line from the psychologist William James that said that when you're born, your experience is just a blooming, buzzing confusion. I don't know if you've ever heard that before. Some of you, like me, might just feel that every time you wake up in the morning. But you just have this sort of confusion of sensory information, right? I mean, it's hard to imagine what that's like. And it's hard to really pay a lot of attention to that remark of James, because you can't imagine being if you wear glasses, as I do, you take them off and you might think, oh, the visual world is a blooming, buzzing confusion, right? What makes it orderly for us? What makes us think that there's a kind of world out there instead of a bunch of things happening to my eyes? Why do we think of it as external? And then, when we might think, well, maybe it isn't external. Maybe it all is happening in my mind. I know in my mind time seems to be passing, but you could imagine at least sitting here thinking, well, I know that time's going by inside my head, but how do I know that all this booming, buzzing confusion of lights is just something on the surfaces of my eyes or in my mind, or is it really out there? In some sense, I can't doubt that time is passing. But is there really a space out there? Or is this all going on in my head? Well, if you love philosophy, maybe you've always thought this was an interesting question. But if you hate philosophy because we ask questions like this, you should realize it really is important. Because if you think about emotion in space, it's motion. It's the sort of moving about in space that gives us the sense of the external world. It's not just that I am confronted by this booming, buzzing confusion, but I can, by my voluntary acts, change my situation and come to an idea of what's the part of the world that's just spatial, that's purely external. Well, if I can take a walk in space and then come back to where I was, that's something I can't do in time. Now you might think, well, this is a very approximate notion that science is critical of, and that's all true, but right now I'm just asking, where does the sense come from that I can separate space-time into its spatial and temporal parts? There's nothing I can do to go back to a previous mental state in time. But I can, at least as far as intuition tells me, I can take a walk in space and go back the way I was, and I can change my perspective on everything and go back to what my previous perspective was. And that seems like an obvious idea now, but that's really, it took a long time for a combination of work mostly by philosophers, mathematicians, and scientists, like working simultaneously on math, perception, and philosophical analysis to figure out that this is the essential idea of the external world. If I couldn't move, I might not need vision, because lots of people have a perfectly good conception of space without vision. But if I couldn't shift my perspective, I wouldn't know what's the difference between a change that's happening in my mind and a change that's happening to my perspective in space. So it's this notion of going somewhere and coming back, that I can execute changes in the spatial world and then undo them. And I can't do that with time, much as we'd all like to. So now if you just think about what does it mean to think about a space-time structure, a trajectory in space-time, it doesn't mean anything more complicated than you see right here. If I think of taking a walk and coming back in space, and I just represent it spatially, it's that figure on the left. If I sort of think of it as moments of time piled upon one another, then I can think of it as that trajectory in space-time, right? At time t0, I was at point x, y. It took me some time to get to that other point, right? And then it took me more time to get back to x, y. It's the same thing that happened, except in this case, on the left, I wasn't thinking about the time. And it's that common sense notion that we don't have to think about the time. Nobody ever thought you could travel infinitely fast and go from point A to point B and back without some time passing. It's just that in common sense reasoning, we think of the time as incidental. It doesn't really matter. Right? We really did go somewhere and therefore change our perspective. And we really went back to where we were. And, it was like a move in a game that we can do and undo. And it takes time, but the time isn't really a factor. It's like, if you have a chess game that you're playing with someone remotely. Now you can do it really quickly on the internet, but, maybe 50 years ago you did something like this by mail. Right? And it was the same game. The moves take time, and it takes a lot of time if you have to mail your move to Australia by surface mail. But the time wasn't really a factor somehow. It's somehow we can ignore that. It's not like putting an ice cube on the table and saying, well, look, no matter what else happens, in a certain amount of time, that's going to melt. But a chess move isn't like that. A chess game doesn't unfold in that way. At least we don't think of it that way. And it's the same with executing a spatial motion. This is our sense of being in a spatial world, that we have these moves we can execute and undo. They can take time, they always take time, but we can ignore the time because the time doesn't matter. Excuse me. I'm just getting over a cold, in case you're wondering if it's anything worse than that. Now, why do we think that there's such a thing called the special theory of relativity that's different from the theory of relativity that always existed. Well, as I said before, Einstein had a view that there was something wrong with the theory of electromagnetism because it didn't respect the relativity theory that was always there. That you had equivalent states of motion in mechanics, but in electrodynamics something was wrong. And this is what fundamentally leads to a new way of thinking about the intertwining of space and time. Now, the basic fact that special relativity started from is something you've all heard of, I think. And that is this idea of the constancy of the velocity of light. Most people have heard something, if only from science fiction, right? Well, you can't travel faster than light. Right? That the speed of light is a constant. That's not really the essential point, though. That the speed of light is finite. Right? That you can't travel faster than light. I mean, people like Newton already knew that the speed of light is finite. Galileo knew too, but he didn't really have a good measurement of it. He thought it was moving too fast to measure by any means he could think of. But by the time Newton wrote his Principia, the speed of light was pretty well known. It was known to be a finite amount, right? Something like 330,000 kilometers per second. And it, as far as Newton knew, maybe something could go faster than light, but maybe it couldn't. Maybe there isn't anything that moves faster than light. That's not really the reason to change your view of time all by itself. It's true that if Newton's theory is true, then you could make something go faster than light. If light's a particle, then if somehow you could swat it as it goes by, you could make it go faster. Because that's part of the Newtonian theory of relativity, right? No matter how fast you're going, when you act on something with a force, it will accelerate. And how much it accelerates will not depend on how fast it was going to begin with. So there's nothing special about the speed of light other than that maybe it's the fastest speed there is. But it doesn't mean that if you had the technical means, you couldn't just make it go a little faster. You just can't. The real problem with light is the idea that the speed of light looks the same to observers no matter how they're moving. It's the invariance of the speed of light. No one believed in that in Einstein's time, except for Einstein. And the reason was because it doesn't seem to make any sense, right? How can a velocity look the same to observers whose velocities are not the same? If you imagine like 3 trains with different velocities, one at rest, one moving with velocity z, and one moving with velocity w. Is there any way for, say, the top one and the bottom one to agree on the velocity of the middle one? How could they agree? How could that velocity look the same to both of them? That would be a contradiction of Newtonian relativity. Well, you can test to see if this is the case. And this is the problem, right? If you imagine a flash of light goes off, right, it goes the same speed in all directions. Why should it do that? Well, light is supposed to be a wave traveling through the ether, right? That means that as time goes by, if you're at rest in the ether, a kind of sphere of light expands all around you. As long as you're at rest, it'd be like if you jumped into a shallow pond full of water, right? Ripples will go out from you equally on all sides if you're not moving. And if you're moving, well, they'll look like they're going faster in one direction than they are in another. That's the problem with the velocity of light. It looks the same no matter how fast you're going. And that was truly a bizarre idea. It just didn't make sense. And this is why Einstein said the reason it doesn't make sense is because we haven't sufficiently examined the concepts that we're using to measure the speed of light, right? Because any description of an electrodynamic system involves relations between rigid bodies and clocks and electromagnetic processes. And in order to give a description of something moving, we have to understand what we mean by time. And in order for ideas about time to make sense, we have to define what we mean by simultaneous. Now, the relation of simultaneous is crucial to the picture I've painted for you so far, right? In the Newtonian world, the reason why we could take this stack and slice it up into its component parts was because we know the difference between what's happening now and what's already happened and what's going to happen, right? The division between past, present, and future is an objective fact about the universe according to pre-Einsteinian ideas. But Einstein asked the question, well, maybe we have to ask what we mean by simultaneity. Can we ask the question, what are the criteria by which we define two events as simultaneous? Right? If two lightning strokes go off, well, can we tell whether they happen simultaneously? Now, you might just think, to make a long story short, well, what's new about Einstein's theory of relativity is somehow that time is relative. That the difference between past, present, and future isn't something that's the same for all observers. If I take the block of four-dimensional space-time and cut it into slices, so to speak, based on what I think is happening at successive moments of time, someone in relative motion might slice it in a different way. So it's not an objective division. But where would he come up with that idea? Because you might think, well, it doesn't really make any sense for time to be relative. You think maybe moments of time and events that happen at moments of time are like numbers and the number line, right? You would just say it's part of the grammar of talking about different numbers, right? Or it's part of the syntactic structure of mathematics, right? You have two numbers. There's only three ways they can be related, right? Either x is greater than y, or y is greater than x, or they're equal. And it's the same with events, or why isn't it the same with events, right? Either when one event happens, right, t1 is later than t2, or t2 is later than t1, or they're simultaneous. You should be able to say that of any two events, right? One of those things has to be true. And in a way, that's a piece of common sense that Einstein's theory does not violate. What it violates is the sense that this relation is objective. That this is a third element in the relation. There's the two events, whether they're simultaneous or successive, and there's the state of motion compared to which they're observed. So the question is, yeah, it seems as obvious for events as it does for numbers that one of those principles has to be true, but it isn't obvious that it's an equally objective relation. Now we know, because we know about the speed of light being finite, and Newton could have told you this, right? That if the sun suddenly turns on or suddenly turned off, we wouldn't know about it right away, right? So for all we know, the sun has just gone out and we're going to know about it in 8 minutes, right? So you can think of that space-time picture. This horizontal line represents the time when that thing happened, when the sun went out. Or suppose that's a supernova. That's, let's say, 300 light years away. That's a little less threatening sounding, right? Well, we know how fast light goes ever since the 17th century. So if we see a supernova tonight for the first time, we can figure out how far away it is, and then we can say, well, there's a point in my past when that actually happened. That event isn't simultaneous with my seeing it. It's simultaneous with some event in my past, in fact, long before I was born, right? What would that be? 1722. I actually can't think of anything really important that happened in 1722, but it was simultaneous with a lot of really important things, right? Just not in my life. And there's nothing really mysterious about that. So you could say, well, if I knew that two events were simultaneous, I'd be able to say, there's a reason why I'm seeing them right now at the same time. And the reason is that they happen simultaneously sometime in my past, and signals from their happening, some trace of their happening, reaches me at the same time. But that by itself is not a good guide, right? I could say, well, look, there's a supernova, and it's 10 minutes to 8 p.m. Were those events simultaneous? Well, obviously not, right? I need this principle that the speed of light is a reliable guide to how far away an event happened, because it's a kind of constant of nature. If I see two events simultaneously, I won't really believe they were simultaneous unless I have some reason to believe that the signals came from equally far away. So for example, if I were to take that picture I mentioned before, I'd say, oh look, this moment was captured. But really, that's not very precise, right? The shutter of my camera might be open for a whole 1/2000th of a second, right? And even longer in somewhat low lighting, right? And that means that's a big interval of time when a bunch of events happen, right? The light bouncing off of each person in the room and every object in the room and coming back into my camera sensor, all of that happened within an interval of time. None of them are really simultaneous, except those that happen to be equal distances from me. So what if you couldn't travel faster than light? Well, this wouldn't have to change the Newtonian picture by itself. Because Newton could have said, I guess you can't travel faster than light. I mean, I don't know how to accelerate a light particle, if it is a particle. But that wouldn't change the picture. That you just have to, you might say to yourself, and this is sort of, this is what was represented in this graphic that Minkowski drew, right? Right, there's now, there's the hereafter, and there's the heretofore, so to speak. Those are clumsy but kind of literal translations of German. But if I couldn't travel faster than light, I guess it's just kind of random whether this scrolling works. Shouldn't have done that, right? The point is, the mere fact that you can't travel faster than light doesn't force you to revise your fundamental ideas about time. So you could always say, well, I don't get to know right now which events are simultaneous. I have to reconstruct it. I have to know, okay, I can't travel faster than light, but I can still figure out retrospectively that this supernova happened at the same time that Louis XIV died. So then I could say, well, you know, there's a kind of division of space-time into if I can't travel faster than light, I can only reach those parts in that upper cone, so to speak. And the only events that can reach me are events that are in that lower cone. And anything to the right and left in this diagram is basically things that I can't influence them and they can't influence me. But that's no reason to think that time is relative. It just means that it's going to be hard work to figure out what was simultaneous in the past. The real problem is, how do you decide whether events are simultaneous? Well, Einstein says, well, let's use this criterion. If I see events at the same time and they happen at equal distances, on the assumption that light travels the same speed in all directions, then they happened at the same time. Right? If I send out a signal, it hits a mirror and comes back to me, I'll say midpoint on my watch between the time I sent out the signal and the time I saw the reflection is simultaneous with the reflection. Now that's a definition of simultaneity that Einstein proposed. But if somebody else is in a different state of motion and they use the same definition, they come up with a different conception of simultaneity, because the same events that are simultaneous for me aren't going to be simultaneous for her, right? So when I draw this line indicating the dividing line between past, present, and future, and when you draw it, we're not going to draw it in the same place. We're going to divide up the space-time world into its spatial and temporal pieces in completely different ways. So in a way, this is basically my point tonight, that why do we think that space and time are intertwined? Because Einstein taught us, and Minkowski made it very clear in this model of space-time, that the world we all know, the history of the world in space and time, doesn't have an objective division into spatial and temporal pieces. That common sense idea I have that I can just undo a spatial change, go back to the way I was, and put everything back to its former state, that's a relative notion. Because my notion of the difference between what's happening now, what's already happened, and what will happen is not the same as that of a person who's in motion relative to me. Now, you could say, a famous example that Einstein gave is a man standing on a platform and a woman moving by in a train, and they're both scientifically measuring whether 2 lightning strikes happened at the same time. The person on the train is rushing toward one of the lightning strikes, and so she'll see that one first and think it happened first. The person on the embankment will see them both at the same time. What's the difference? Well, you might just say, well, she's wrong. Because she's moving, she didn't get to observe correctly which of these 2 events happened first. She thinks one happened after the other, but in reality, they happened at the same time. But that's a judgment you could only make if you were sure you knew which one of them was at rest. The fact that we can do all these experiments and we fail to detect differences in the velocity of light means that just like, say, the person on the moving ship with Galileo, right, they'll pass what you thought was a test for being at rest, the ball falling down alongside the mast or the stone falling from the tower. It's not a test of being at rest because you can have 2 observers in relative motion. They both pass the same test for being at rest. You might consider that incoherent. You might say, well, if this definition of simultaneity means that the division between past, present, and future, the separation of space from time, turns out to be relative, maybe I need another definition of simultaneity that will show me which events are truly simultaneous and will truly divide space and time into their objective spatial pieces, spatial and temporal pieces. Now, Einstein's reply to that was, in effect, well, you tell me what you mean by simultaneity. Give me another definition that makes that work. And Einstein's view was, the definition I'm using is the one that we use in common sense. We think events happen at the same time when we get a signal at the same time from them. That's our visual intuition of simultaneous events. We saw them at the same time. We think we caught a moment on our camera because, well, all these events there were signals created by light, right? Light signals all came into the camera in a small interval of time. That's our intuitive notion of simultaneity. It's just that when we try to extend common sense to a bigger picture, we find that my common sense picture and the common sense picture of someone who's in motion relative to me don't agree. They don't fit into a coherent whole. And that's the kind of refinement of common sense that theoretical physics has been doing since at least the time of Galileo. And you might say, well, if it's so commonsensical, why doesn't the world look special relativistic? Well, in a way, it does. Because we don't experience anything that violates the special relativity theory, right? The thing is, our lives are just so slow compared to the speed of light that we never get to do these experiments in everyday life, right? The time that it takes light to go from where we are to any place that's really relevant to us and back is so tiny, right? It wasn't until you had sort of telegraphy and, for really vivid examples, right? People up in space receiving, or on the moon, receiving radio signals. Then you had to think about the time it takes for things to happen. Our lives, however, take place so slowly compared to the speed of light over such a small area of space compared to how far light can travel in, say, a second, that we don't see from our immediate common sense perspective how it will fit into a bigger picture. We don't know anyone personally who's moving away from us at a speed approaching the speed of light. But when we do, we don't find that a common sense is violated. What we find is that a refinement of common sense with the help of theoretical physics puts it into a larger, more coherent picture in which space and time, in spite of what seems obvious at our local level, really are intertwined. So I'll stop there. Thank you so much for your patience.
Thank you so much, Robert. I just turned it on? Yes, thank you so much. So I will be bringing the microphone around for questions. And even though it's a refinement of common sense, that doesn't mean it's easy. So I'm sure that a lot of you will have questions. Yes.
Thank you very much for your talk. One of the things, like learning about Einstein's relativity, theories of special and general relativity, one of the things that I've always wondered about is with the Earth spinning on its axis, going around the sun, going around the Milky Way, and the expansion of everything, the concept of relative motion and even our measurements of the speed of light, how, like, do we currently incorporate or factor the measurements that we may not be able to measure, like how quickly we're moving throughout the Milky Way, and then how quickly the Milky Way is moving in relation to like the epicenter? Do we factor those kinds of movements into our calculation of the speed of light?
Well,
or does it matter?
In a way, it doesn't matter, right? I wanted to go back to one of my previous diagrams, but I guess I was evil in a previous life or something. So this is, when I was talking about the Newtonian, one of the beauties of Newtonian physics was this idea that, we're trying to figure out what's happening in the solar system, or at least he was. How are all the planets interacting? Where's the true center? Right? What are the forces holding all the planets in orbit? And he figured out, thanks to that extended sort of quasi-relativity principle, right? We could ignore all that, even though the thing is, even though the whole solar system might be revolving around something, as we suppose it is now. We can ignore all that because we have this internal picture that isn't going to be affected by an external force unless that force acts in a non-uniform way. But then we'll notice that, right? Just like the people who live on Jupiter don't notice because the moons of Jupiter revolve around Jupiter as if nothing was affecting them at all because it's so far away from the sun. But we notice the difference that the sun makes to us and our moon because we're so close to the sun, right? That the difference between what the sun is doing to the moon and what it's doing to the earth really matters. So that's one part of the answer. Yes, we can ignore a lot of these things. Another thing, though, in a sense, the things we can ignore are things that can really matter to technology. Right? We have to make relativistic corrections to things like clocks and satellites. This is the one, apparently, as far as I know, the one technological use of general relativity, except the relativity bomb for us. Oh, I wasn't supposed to mention that. When I was in graduate school, my friends who were in graduate school in physics would say, we have to try to tell the NSF that we're working on a relativity bomb so we can get funding. But as a matter of fact, if you don't make corrections in the times of satellites, the GPS satellites, in accord with the motion of the Earth, the rotation of the Earth, the relative velocity of a satellite and the Earth, if you don't make relativistic, special and general relativistic corrections to that, then all of your GPS information would be off. It would accumulate errors of something like 10 kilometers a day or something. I forget what the figure is, but it wouldn't be very reliable if you didn't make these corrections. So sometimes you can ignore them, and sometimes you can't. It's another beautiful thing about the Newtonian way of doing physics, as I think Bill Harper would tell you, right? whenever something goes, whenever there's some mismatch between theory and prediction, it just means you learn something new about what factors are at work.
Great. Further questions?
It's a silly question.
No,
What
no questions are
no,
silly,
no.
just my answers.
Well, what you just said, it brings to mind, the terrible earthquake and tsunami, the one that, 2004, 2005, I can't remember the year. And they said that was so powerful, it slightly altered the orbit of the Earth. So they would have had to account for that with the satellites for the GPS, yes?
I would think so.
Yeah.
I'm not personally aware of that, but I would think that you would.
Yeah. No, it's astounding.
Sorry, did you want to?
I was going to suggest an answer to that. I have a friend who works for the United States Naval Observatory, and they use data from radio telescopes to measure distant quasars. And they use that to then time the Earth's daily rotation to something like 12 decimal places. And they can actually tell when the weather forecast says there's a storm coming from the Pacific Ocean that's going to hit the Rocky Mountains, the Earth speeds up enough that they can tell that difference. So they can make those measurements at that level, and that's where it's important to include those factors. That wasn't a question.
So that's something that goes back to Newton too. The idea that you start out by thinking the rotation of the stars is a kind of perfect clock as they rotate around the Earth. When you realize the Earth is the one rotating, and you could think, well, the Earth is a perfectly good clock, but you have other things that you can compare the Earth to, right? You can compare the time it takes the Earth to go around its orbit to the time it takes to rotate once. And you can say, well, we have better and less accurate ways of measuring, and we can actually think about the rotation of the Earth as a measurable quantity that slows down or speeds up, because we have some other standard we can appeal to. Right? It's another kind of refinement of common sense, really, because we start that ordinary common sense comparing what we don't think of as a reliable clock to what we do think of as a reliable clock. Like if I think my watch is saying it's 11 a.m. and the sun is at its highest point in the sky, I'm not going to say, oh, the solar system must be out of whack, right?
I thought there was a question over here that somebody had a hand up briefly. Am I wrong about that? Oh, yeah, sorry.
Thanks for your explanation about space-time. Does that have anything to do with entropy?
Well, not specifically. Of course, entropy is one of those, the idea of the quantity of disorder, so to speak, increasing as time goes on. That's one of those things. There isn't anything built into the space-time picture that tells you the difference between the past and the future. Right? Even the Newtonian picture, you could say, well, I could sort of turn every molecule in the universe around and run everything backwards. Right? You could, make the whole solar system go backwards if you could apply the right forces. But entropy, right, the sort of the decrease in organization seems always to go in one direction. And that seems to be independent of which model of space-time you have.
Yeah, last week we learned about time going backwards.
Right.
Kind of what triggered that.
Well, some people think that's why we remember the past, right? We can't go backwards because we can't go back to a state before the state of our brains was altered by our perceptions, and right, we can't turn memories into perceptions again. In spite of the fact that I can walk 3 feet in space and walk back to where I was.
Other questions? Yeah.
I actually don't have a question. I just have a comment. You taught me early modern philosophy 30 years ago.
Oh.
So this is bringing back a lot of memories. I can't believe I actually understood all that stuff back then because this is very deep, but I just wanted to thank you for your lecture tonight and for teaching me that many years ago.
Wow, you don't look like you could possibly be old enough to.
Thank you.
But thanks very much.
But is the lecture better tonight, or
Have I gotten any better in 30 years?
Yeah, just got a bit of mileage, but didn't get any better. Yeah, I was wondering if you think that that there is a point after which we kind of cannot relate our common sense to physics, or physics stopped being an extension of our common sense? Or would you say that still in a way our best modern physics is an extension of our common sense?
Well, in the specific way I meant it, I would say yeah. But then when you say physics violates common sense, it just means that you have a natural tendency to extend your common sense view too far, right? So we say, well, everything looks flat around me, right? But ordinary refinement of common sense usually means, well, you know, sure, maybe the whole Earth's surface is like that, but I find out it's not, right? So really strange things happen in quantum mechanics, right? And you might say, well, you might not think the world is so strange if you're in this laboratory doing these experiments and seeing how the statistics come out. It's when you ask yourself, well, what if another experiment is being done with half of the atoms coming out of this oven? And what happens when I compare the statistics they get to the ones I get? And then I can't fit it into one common sense space-time picture. You know, some people think Niels Bohr was kind of kooky when it comes to philosophy, but I think this is something he put rather well. We do an experiment here, and we can describe it completely. What we don't have a right to assume is that when we try to put these results together with those results over there, we'll get one coherent picture. And science is always doing that to common sense. And so quantum mechanics is weirder than, well, I was about to say it's weirder than Newtonian gravity, but I'm not really sure about that. Certainly, Newtonian gravity was regarded as weird in its time as quantum mechanics is in the past 100 years. Right? It's just that's what science is always doing to common sense. Right? Putting it in a larger context where you realize some of your assumptions about how easy it would be to extend your common sense picture turn out to be wrong. Light's just a velocity. It's a really fast velocity. That means it's somewhere in between 0 and something even faster, like maybe gravity. Maybe gravity goes infinitely fast, or maybe it goes a lot faster than light. And light's just a kind of, you know, the velocity of light's just a velocity in that spectrum somewhere. Well, no, it's not. We just assume, right, that if somebody was moving relative to me, we could make some calculation about the speed of light to figure out, for a moving observer, the way we might think of, say, a far-away observer, which events happened at the same time. Right? If I send a signal to a spaceship and they get it in a year because it's a light year away, all they have to do is know how far away they were when they got it and the speed of light, and they'll say, oh, I know when it really happened, right? And if the speed of light behaved like a normal velocity, you could do that with two moving observers. Well, okay, tell me how far away you are and how fast you were going when you emitted the light signal. I'll be able to calculate in my time when that event happened for you. I can set my clock to yours. But science, this is just another example of science telling you, well, that assumption that you make, that you could always correct for a velocity of light the way you could for any other velocity, just turns out to be wrong. And so, yeah, science tells you that common sense is wrong in a way, but it doesn't tell you your common sense picture is wrong. It tells you you were wrong to extend your common sense picture too far. You assumed that the common sense picture had a simple extension to a large-scale picture. You know, like you assume that the geometry you do on a piece of paper would apply to the whole solar system, right? Otherwise, people like Kepler and Newton couldn't tell you about the areas of huge cosmic triangles, right? They just assumed it's the same geometry that works on a piece of paper. But it would be wrong to assume that that would be true on any scale, right? It's not violating your common sense picture. It's violating your sense of how easy it will be to extend the local common sense picture to something global.
Thanks.
I wanted to, okay, I might be very sloppy while explaining it, but I was, when you were explaining the space and time graph, I was thinking, what if, so time is going perpendicular, what if it was going through an angle? Then the space S1, S2 would be perpendicular to the new time axis. Then will at some point because T1 is remaining same in both cases, will at some point the S1s collide because they are at an angle. One is like this and one is like this. And it will seem like for this person, he's at S1 at a certain place where I already passed like a few minutes ago. Was I clear enough? Maybe not. I'm not
No,
sure.
that's exactly what's happening with the relativity of simultaneity. Right? If I look at this picture and I say, well, because I timed how long it took a signal to come back from a reflection to come back from a mirror, I'll say the reflection was simultaneous with halfway through that time on my watch. Right? Now, if Newton were correct, everyone would agree that all those events happened at the same time. Einstein's theory is based on starting off with the idea light has the same speed for everyone, and let's use light signals as we do intuitively as a criterion of simultaneity. And that's where you get exactly this sort of colliding of two, not what they are, when you say they collide, it's not like a violent collision.
It seems like the person who's going this way will think that in time T1, I actually overcome more length of more space or more distance than this person did.
Well, in a way, that's just right? So if this is your state of motion, right, my state of motion is in a sense orthogonal to or perpendicular to the events that I take to be simultaneous. When you do the same, you use the same definition and you find, well, this event that I think already happened before the reflection, you think happened at the same time. So this is space at that given moment from your perspective.
Yeah.
So that's exactly what relativity in Einstein's sense means, that we don't agree. Events that I think happen simultaneously, you think happen one after the other, and vice versa. And so that's why we say there isn't an objective way to slice time up, so space-time up into space at given times. Right? I'll do it differently from you if we're in different states of motion. And therefore, we actually simply won't agree on this. My S1 won't be the same as yours. I have another diagram which I didn't really get to. I don't know if this is going up or down now. So if you think of, if you think in the Newtonian case, right, you would say, it doesn't mean anything to say, well, the histories of those observers represented by F1, they're perpendicular to time and the other ones aren't. Because you could just redraw the diagram. You say, well, actually, no, they're moving, right? And we're at rest. There's no such thing as being, because everyone agrees on the same time, there's no such thing as someone's path through space-time being perpendicular to space. It's only in Einstein's theory you say, well, actually, that's a representation of the relativity of simultaneity, because the simultaneous events are, so to speak, perpendicular to my path through space-time, and different events are perpendicular to your path if your path isn't parallel to mine. And so you have a situation like this. The yellow is supposed to represent light traveling at the speed of light. I think certain events are simultaneous and you don't, but we agree on the velocity of light. So things that happen one after the other for you might seem simultaneous to me.
So we have another question back here and then one here.
Yeah, I'm just trying to process the question and the answer. I'm wondering if this has anything to do with the uncertainty principle, Heisenberg's uncertainty principle.
Well, I would say not, because that's a principle that seems to be independent of relativistic considerations. It was developed before, it was developed independently of a relativistic form of quantum mechanics, right? It conceivably could be made compatible with a new form of quantum mechanics in which we dispense with relativity, with the relativity of simultaneity altogether.
Okay, we have another question here.
So building off of her question, the expansion of, I guess, space-time, I was always confused about how everything could be expanding at the same rate everywhere in terms of physical space. So the fact that this is possible, or this is the way that it is, does this mean that that time is also space-time is also expanding at that constant rate, as well as, I guess it does?
Well, I don't think it makes, in a principal way, a difference to the picture of time I've been presenting. But what you have to, the way to think about this picture of time is, Einstein's special theory of relativity is a really good picture of a small piece of the universe, right? So the idea of space-time expanding is a notion that comes from general relativity, in which you actually think of space-time as being non-uniform, not only sort of as distributed at any given epoch in history, but as it unfolds through time. So in a sense, you could think of, actually I should hand this one over to Chris, who knows everything that a philosopher can know about these things. But
yeah, I was just thinking like the comparison of one perspective to another person's perspective, and how one appears to be kind of veering off diagonally, but the same goes for the second person's perspective.
Well, there's certain things you could count on. On the one hand, you could say, well, if the universe has a history like that you could measure, then that kind of gives you a universal way of thinking of time unfolding. You could think that way. Mm-hmm. It's not required. At the same time, in an expanding universe, it still is the case that relatively moving observers who are close enough in the universe to sort of track each other can still find that their clocks don't agree. And that simultaneous events for one aren't simultaneous for the other. Mm-hmm. So the global picture introduces a lot of interesting questions, including the idea of a kind of unified history for space-time. But it doesn't change the local facts about special relativity all by itself.
Yeah.
Great. Well, thank you all for coming, and thanks so much for your questions. And let's thank Robert for this.
No, thanks again for your.
Of how space and time are intertwined.
Thank you for your great patience.